shows.
This is the sugar of champions. We're addicted to series.
For the studiation shows.
Okay. There's another method I sort of want to show you guys. Just want to get through this quickly. It's just, let's see. I'm going to redo the last example. I have to sort of set up the context. There's another way we can formulate series solutions, which this will actually prevent, we won't have to like shift the indexes if we think of it this way. Is to think of y as, this might seem weird to some of you, but you can actually start a series from negative infinity to infinity. It's more common in more advanced classes, but we can work it here with an equals 0 for n less than 0. Right? So you define all the negative terms to just give you 0 as the coefficients, right? And so the idea is now, if we're starting to shift the n's, it won't matter, right? If I shift 2 more into negative infinity, what's the difference, right? It's sort of, I don't have to shift the index now if I sort of think of things this way. And it would still end up giving me what I expect, right? That this will still be the series, right? Because of this definition. I just defined all these terms going back into infinity to be, going back to negative infinity to be 0, right? So I'll still get something that looks like a regular series, but now with this, I don't have to shift the index. And how do we get around that? Well, let's redo that example from the final. No, that was not it. This was x squared. X squared and 1 plus x. Right, x naught equals 0 and all that, and we have that. We're given y of 0. Okay, compute the first 4 terms involved. So now we're going to sort of use this idea. So this will give us 3 times the series from minus infinity to infinity of n minus 1 a n minus series from minus infinity to infinity n minus 1 a n, that's the n minus 1, minus sum from negative infinity to infinity of n a n, that's the n plus 1, plus series from minus infinity to infinity of a n x to n, plus the series from minus infinity to infinity, a n x to the n plus 1. So now we can just, we still have to get all of our powers to be the same, that's fine. But now, the bottom limit's not going to change. It's going to look the same. So I'm going to shift all n's to n plus 2's. Minus, well, let me just start. Once I change all the powers to be the same, they're all going to have the same index, so I can start throwing them into the big series. So this is, if I take big series from infinity of 3. Here I'm going to shift all n's to n plus 2's. I'm going to throw that x to the n all the way up above. Here I'm going to shift all n's to n plus 1's. Here I'm going to shift all n's to n minus 1s. Here I don't have to shift anything. Here I have to shift all n's to n minus 1s. Okay. So the indexes don't change. I don't have to worry about shifting the index, which means right now I just simply jump right into the recurrence relation. So now I will be able to solve for a n plus 2. This is going to cancel at 1. This I bring it over, so this is n times n plus 1, a n plus 1, plus n a n minus 1, minus a n, all over 3 times n plus 1. And again, those are themselves, but now I'm going to compute everyone from the recurrence relation, right? Your recurrence relation should coincide with what you would have gotten if you had popped out the terms and evaluated. So that's why we can get away with doing this. By the way, last time I think I put a plus here, it should have been a minus. I don't know why no one caught that.
Okay. You're our professor.
So, now to get a2, we simply plug in n equals 0. This term will die, this term will die. But even if this term didn't die, my an minus 1 when I plug in 0 would have been 0 anyway, by the formulation that we have now. So this is 0, this is 0, this is minus a0 over this is 0, this is 0, 6. And you'd realize that's what we got last time. And if we say a3, what's a3? This is when we plug in n equals 1. This would give us 2a2. N equals 1 would be a0 minus a1 all over, plug in 1 here, that's 2, 3, 3, that's 18. I replaced the a2, so this is going to be minus a0 over 3 plus okay here. This is a plus, this is a plus, this is a minus. We should be getting the same things we got last time. Which this is looking good. Was this a plus?
You're asking us?
Just want to make sure my signs are right.
Don't screw up.
Looks okay, right?
Yeah.
Okay, so this would give us what now? And plug it to get 3. What?
From last, when we did the other way, it was minus.
This was minus?
Yeah.
Because I got the signs wrong last time. I want to make sure we're
Oh,
okay
okay.
this time. This was plus, this was minus, this was minus, this was plus, this was plus, that went away. So move that over, that's a plus, move this over, it's a plus, move this over, it's a minus. That's okay, right? You're okay up to here. Our A0 was 0, 0, minus A0 over 6. Okay, that's fine. So now for A3, I plug in n equals 1. This gives me 2A2, n equals 1, gives me A0, n equals 1, gives me A1. Okay, so now what would we have? I don't seem to remember getting this answer last time we were there. I seem to remember getting a minus 2 over 27 here.
Yeah, it was minus. That's that.
Yeah, so what happened here? Why did we lose a sign? These two came from that. This minus got here.
So it's the other way.
And this is plus and this is plus, right?
Yeah.
Did you copy the correction, the question correctly?
That could be
Yeah, I feel like we are on the same term.
Yeah,
It's
yeah.
supposed
I
to
pulled
be
an Eddie.
plus.
This was a plus.
Damn!
Don't you love
this
the way
is
I
a
can
plus.
nail that?
So this is a plus.
She knows you very well.
That's what I do all the time.
That's what I have to tell her all the time. Did you copy down the question correctly, Eddie? Jeez, it's 8 a.m. Trying out loud.
No excuses, Professor. Isn't that
That's
what you
right,
tell-
Vincent.
Isn't
No
that what you,
excuses.
isn't that
Okay.
what you tell me?
So this is plus, which makes this minus, right? Which makes this minus, which makes this minus, and then we would actually get what I thought we should get. Okay, so this is minus 4, so this is minus 2 over 27, and everything looks nice, and we can plug it in now. Or y equal to a0 plus a1x plus a2x squared plus x cubed. Because the x is up to 4 terms, so we're only doing 4 terms. Our a2 is minus a0 over 6. Our a3 is minus 2 over 27 a0 minus a1 over a2. And now we can put in our initial conditions. We know that y of 0 is minus 6 and y prime of 0 is 2. This gives us that y is put in minus 6, 2x, minus 1, well plus 1 now. A is minus 6, right? So this gives us plus 1. Six, 3 to 6 goes 2 times. A1 is 2. So we have brackets, which should be the same as we got last time. A0 is a minus 6, so that becomes plus 6. Okay. So you see what this does, by assuming that we can run our series all the way down to negative infinity, we don't have to worry about shifting the index and evaluating terms. You can sort of just jump to the recurrence relation. The thing is, the recurrence relation should be consistent with all the other equations that you've got anyway, right? So you can sort of ignore those parts. Although, when we get to 5.5, there is going to be some virtue to evaluating terms. It's going to be a way to check your answer, because there's going to be something that pops up that you should be looking for. But, you know, if algebra scares you, you can use this to get out of some of it. Just a word on 5.3. We don't focus on this too much in this syllabus, and it hardly shows up on a final, but I thought I'd talk about it anyway. Just one little itsy bitsy series solutions. Ordinary points. Part 2. Y. The notation that they call y in this chapter is phi of x. X minus x naught to the n. Infinity. once we know a power series, we actually have a formula for the coefficients, right? Back in Calc 3, we learned about Taylor's theorem, which means when we're given a power series, we could have a formula for the coefficients, which was...
Say it. We're not going to have it. X equals x negative 45.
F to the n series.
That's
With
right,
squared.
e to the n derivative
I was close.
over n factorial. I'm not going to derive that for you again because your Calc 3 professor should have. I know I did, which means Nazif and Tasnim should know.
You talking to me?
Okay, so we can actually find the coefficients this way, right? Just by using Taylor's theorem. So this helps us with nasty looking series problems like this one. Y double prime plus sine of xy plus cosine of x. So we can take a moment to appreciate
The sine of cosine.
the challenges of solving this problem by a series solution. No technique that we've done before will work, certainly, because that's just crazy, having trig functions as your coefficients. But then you're like, okay, let's do a series solution. And then you're like, well, that means I have to be able to write all these as series. Right? So I have to find the power series for sine, power series for cosine. But what this means is I'm actually multiplying two infinite series. Right? So if you wanted to do the algebra, that would be crazy, right, to the first four terms or anything. That's still really crazy. But this actually spares you the effort, right? Because you can know that y of 0 is equal to a0, y prime of 0 is equal to a1. Here what you can do is you can actually solve for y double prime minus sine x times y prime minus cosine x times y, which means then that y double prime of 0 is equal to, I can just plug in 0 here, right? So that would die. This would be minus y of 0, right? Just by plugging in. Cosine of 0 is 1. This would be y of 0. Y of 0 I know is a0. Right? This means that the second term is just going to be this guy over 2 factorial by that formula. I can then try to figure out what is y triple prime just by taking the derivative of this. Using the product rule here, I would get minus cosine x y prime minus sine x y double prime plus sine x times y minus cosine x times y prime. This would mean if I take y triple prime of 0, this would give me minus y prime of 0. That would be 0, that would be 0. This gives me minus y prime of 0, which is minus 2y prime of 0, which is minus 2 y prime of 0 is a1. Which means the third coefficient is given by minus 2a1 over 3 factorial. Or 3 factorial is 6, this is just minus a1 over 3. And I can just continue this, just keep differentiating this, plugging in 0 and finding all the coefficients by dividing the results by n factorial. So this would give us, our series solution should look like just a0, a1x. Our a2 was this, minus a0. Our a3 was this. can find a solution that way. Right? Just by remembering this formula to get the coefficients, you can just solve for the y double prime, keep differentiating, and you can use that to find the ans. So that is just another way. So that was very rarely asked. It's asked on more like the older finals, and you have some homework problems on it, but that is a method. In the case where you are specifically asked for a recurrence relation, this of course wouldn't work, right? So some of the questions they'll say, find the recurrence relation, or find the recursive formula. Then you couldn't do it this way. But if that's not specified and they say, find the solution, this is a possible method. Right? So just want to show you what some options that you have. Like I said, not going to dwell on that because it's not really a focus. And they usually do ask for the recurrence formula specifically, so let's move on. We have a few homework problems on that. It shouldn't be that bad. It's just successive derivatives. Euler.
There.
Euler 3 times fast. And regular singular points. Now this is going to be very familiar to you because we've actually touched on these guys in chapter 1, but we never sort of explained where they came from. Did I actually tell you guys what singular points are?
No.
No, I should probably do that first. So remember what an ordinary point was? Gx prime plus Rx y Gx. Point x naught for which p of x naught equals 0 is called a singular point. So remember, an ordinary point was where this was not 0. If it is 0, we call it a singular point. Why is that point important? Is because if we put this in standard form, we're going to divide through by p. Dividing through by 0 is a problem, right? So points where this sort of thing happens are points of interest, right? And if you start to graph the solution to this differential equation, crazy things start to happen at this singular point. They shoot off to infinity, or they disappear, or they just oscillate super fast. Like crazy things happen here. Right? There are points when things are not so crazy, and those are called regular singular points. Right? There are other places where things get super crazy. We call those irregular singular points. But singular points in general are of high interest to us because crazy things start to happen there. Next thing I want to use Euler's equation. So there's a kind of equation that has a regular singular point that is of very importance. It's called an Euler equation. They look like this: alpha x squared, y double prime, plus beta x prime, plus gamma y equals 0. They sort of look like quadratics, right? You have an x squared, you have an x, you have a constant. Right? And these alpha, beta, gamma are constants. alpha not equal to 0 in order for it to be an Euler, right? It has to start with an x squared to be an Euler. The other coefficients have to be polynomials, but when they're specifically in this order, x squared, x constant, looks like a quadratic, we call that an Euler equation. Now, way back in chapter 1, they introduced this. They never really told you anything about it, but they sort of gave you the method to solve it. Anyone remember what the method is?
e to the I pi.
Nope. Doesn't involve exponentials.
X to the n.
Assume y equals x to the r, right? Now remember, why is it that we chose the exponential in the first case, back when we started to figure out why we chose the exponentials, is because it allows us to get similar terms, right? When you have the constants here, then all the derivatives, you want a function where all the derivatives will be similar and you can combine them and get like terms. The exponential was the best one to choose. But now, knowing that we have polynomials here, the exponential is no longer the best thing to choose, because you can't combine an x e to the x and an x squared e to the x, right? So the exponential is no longer the best choice. Now the choice seems to be, why not choose polynomials since they have polynomial coefficients? And so they chose this to be the solution, right? Now, given that, this would mean that y prime is r x to the r minus 1. It also means that y double prime is equal to r times r minus 1, x to the r minus 2. Plugging this into the ODE. We get, so we start to plug these guys in here. We get alpha x squared r times r minus 1 x to the r minus 2 plus beta x r x to the r minus 1 plus gamma x to the r. Now something curious will happen here. We can combine the x's. So this gives us alpha r minus 1
X to the
x to the r plus beta, can combine the x's here, r x to the r plus gamma x to the r. So now our x to the r is a common term. Now, notice something. What this means is either x equals 0 or alpha r minus, or alpha r times r minus 1 plus beta r plus gamma equals 0. However, what can you tell me about x equals 0? Based on what I said earlier.
Well, it can't.
Is a singular point.
You got a point like further left.
We'll deal with this later. By later, I mean 5.5. This later, right? Because it's something that you have to deal with. Otherwise, we are at, right, x equals 0 is the only singular point to this, because if you put that in standard form, you divide through by x squared, you'd have just a power of x in the denominator. Otherwise, we're at an ordinary point, and we obtain this guy. Very important equation. It's sort of like the characteristic equation for an Euler equation, but it's called an indicial equation. Why? Because it gives you the power, right, which is called an index. Or indices are called powers. So this is the equation that will give you the power of x that you need to solve. So it's called an indicial equation. So in the case of where we're around a singular point, we have to tread very carefully. We actually need series to solve it in this case. If we're not at a singular point, then this is true. We'll deal with the singular point case in 5.5. But for now, let's look at the case where we don't have a singular point. We proceed assuming x is greater than 0. If x less than 0, don't worry too much. All that means is then replace x in the following. By absolute value of x. So if your x is negative, replace all your x's with absolute value of x. It'll fix everything. Okay. But let's assume x is positive, so we can just keep writing x. So this is always something you have to look for. They'll always tell you whether you're at the singular point or not, or you should assume x is greater than 0 or less than 0. I want to get to some examples, but I have to tell you what these are. The initial equation is quadratic. And what do we know about quadratics? As far as their solutions are concerned, there are only 3 possibilities, right? First case is if you have unequal real roots, right? Unequal real roots. Say R1 and R2, right? So you solve that initial equation, it's a quadratic. Suppose you get 2 answers. Then that just means your y is equal to C1 x to the R1 plus C2 x to the R2, because you assume y equals x to the R. There's a second case where you have a repeated root. Let's say R1 equals R2 equals R. In that case, you can use reduction of order. Assume that the second solution is a function times this one. You run through the process. Ultimately, which I don't recommend ever doing this. It's really, do it once, but don't do this on a test because it gets really messy here. Ultimately, you will end up with y is equal to C1 x to the R plus C2 x to the R ln x. It turns out that your v, after doing the reduction of order, will end up being ln x. And like I said, if your x were negative, you just put an absolute value here, it'll all be consistent and work out. The third case is we have complex roots. This means your r is equal to a plus or minus ib. In that case, we have y is equal to c1 x to the a cosine of b ln x plus c2 x to the a sine b ln x. Now that one's probably sort of weird. Y, if you assume x is equal to a plus or minus ib, what we do here is we rewrite this as e to the ln of x to the a plus or minus ib, which we can write as, the log allows us to bring this power down in front. So this is a plus or minus ib times ln x, which is e to the a ln x times e to the I b ln x. This guy can move the a up, so this guy is just x to the a. This guy, however, Euler's formula applies with b ln x being the angle. So you get cosine of b ln x plus I times sine of b ln x. And then you put in your arbitrary constants. So that's sort of why it would look like that. But those are the three possibilities. That's the theory. So you have to know what an Euler equation looks like. You have to know what the initial equation looks like, which I erased also, and you have to know the three situations, just as before. You know, when you assume y equals e to the rt, you had those three possibilities. You had to just know them, memorize them, apply them. Right? That's what we're going to do now. Find the general solution. First one, x squared equals 4x. Have the third one, but let's do these. Okay. So you're faced with this problem. They might not tell you it's an Euler equation, but you should recognize it. X squared, x, constant. It's sort of like there's a quadratic built into this differential equation, right? Where the second derivative goes with the squared term, the first derivative goes with the x term, the original function goes with the constant term. So you're like, oh, that's an Euler equation, which means all you do is you jump into the initial equation, which looks like what?
X squared plus x to the r.
Remember, the coefficient here is 1, that's your alpha, that's your beta, that's your gamma. So you do alpha r times r minus 1 plus beta r plus your gamma. This is going to be r squared. This will be minus 5r plus 4 equals 0. This, I think this factors 4 and 1 maybe, minus and minus. So we get r equals 4 or r equals 1, which means y is equal to c1 x to the 4th power plus c2 x. Right. Any questions? Try another one, this one. So we look at this one and we see it's also an Euler equation because it has the quadratic form. Okay, so what do we do in this one?
R squared.
Same thing, right? Alpha is 1, beta is -3, gamma is +4. So it's alpha times r minus 1 plus beta times r plus gamma. This gives us r squared minus r, that's minus 4r plus 4 equals 0. This gives us r minus 2 all squared. So I get a repeated root. So this means y is equal to c1 x squared plus c2
X squared ln x.
There was a problem here. We can see what the problem here was.
It's
Very
for
simple.
x.
We define x to not be 0, which means
Also,
it's
absolute.
positive to be negative, which means we have to, well, the x to the fourth won't matter,
So,
but you should do that just in case. Okay. Same thing here, we assume x should not be 0, which means negatives are possible, so we should by right be doing this. The x squared in absolute won't matter, but it will matter in the ln. So that's that solution. Yes.
So when we have repeated root, we just had ln x.
Yes, you can attach an ln x to it. It's just like how back in the day you just attach a t to something.
Yeah.
In the case of Euler equation, you attach ln x to it.
Oh.
Just because of how this works out, how it works out with the x to the r. Basically, you always do something like this where you introduce the exponential and apply the rules you know for exponentials, but that throws an ln into the mix. So that's sort of what it is. Here x is greater than 0, so we don't have to worry about the absolute values. How do we solve it? What's the equation? 4r r minus 1 plus 8r plus 17 equals 0. So this would give us 4r squared minus 4 plus 8 plus 4r plus 17.
4 plus 8r, which is 12.
It's a minus sign.
Oh, sorry.
So now what? How do we solve that? Does that factor?
no.
Doesn't factor, we have to use the quadratic formula, so it's minus b plus or minus the square root b squared minus 4 times a times c all over 2 times a. So this is minus 4 plus or minus 16 is a common term. I can factor that out. That becomes a 4 outside here, and I would be left with 1 minus 17 minus 16 over here. 8. So this becomes minus 1/2 plus or minus, radical 16 is 4, 4 times 4 is 16, huh? 2i. So that's a complex. And therefore, our general solution should be c1 x to the 1 minus 1/2 cosine of 2 ln x plus c2 x to the minus 1/2 sine of 2 ln x. If negatives are possible, I'd put absolute values on all these x's. So that's just another technique to learn. The really bad case where we want to solve the solution super close to x equals 0, we'll need series for it. That's the next section. Right? But as long as we're away from 0, this is how things will work out. Assume y equals x to the r, get the initial equation, and based on what your solutions look like, you have 3 possibilities. Just apply a formula. So now, So we have singular points there. The not so crazy ones, these are ones we sort of have techniques to solve, which we will do in this class. The not so crazy are called regular. And the crazy ones are called irregular.
How crazy are we talking?
Crazy, like outside of our scope, crazy, you'd take a graduate class in differential equations to figure out how to deal with them. We're only going to focus on the regular ones, but we need to recognize when they show up. So I'm going to tell you how to know when something is regular or irregular. Given p of x, y, double prime plus r of x, y equals standard form. Basically, you want to make sure these guys are well behaved enough as x is approaching 0. Let's see what well behaved enough means. Well, suppose x naught is a singular point. i.e., p of x naught equal to 0. So we have a certain tolerance for how bad things can get, where we can have a series solution very similar to what we've been doing existing. Outside of the scopes, we need to do something else, or the solution just might not exist at all in series or any other form. Suppose, okay, so x is a singular point. Here's how you deal with it. If the limit as x approaches this point of x minus x naught times p of x over p of x exists and is finite, and at the same time the limit as x approaches x naught of x minus x naught squared of r of x over p of x exists and is finite. Then x is called a regular singular point. Those of you with a lot of insight into Calc 1 would realize that this sort of means that this guy behaves sort of like 1 over x, which is not too crazy. This guy would behave sort of like 1 over x squared, which is still not too crazy. When you get to like 1 over x cubed, functions behaving like that, it gets too crazy, basically. So you might be required to simply identify when something is regular or irregular, which means you just check those two limits as long as they work out. I should put otherwise. X naught is called irregular. So if you take these limits, they give you an answer, a finite answer. It's a regular singular point. It means things don't get too crazy. If you take these limits and you get an infinite answer, the limit doesn't even exist, it gets too crazy, right? Basically. Okay, so. We only have time to just do some tests. And then next time we start with 5.5 and do the series solution for the regular singular points of an Euler equation. Determine and classify singular points. So that's an Euler equation. This is something that's almost an Euler equation. If this x wasn't there, it would be an Euler equation. This is the kind of guy we can solve with series. That kind of guy we don't need series, just use y equals x to the. But that's coming attraction. One more example. We're going to go through all of these and then get out of here. Squared 1 minus x squared is 2xy. So it looks like our next test is going to be Monday after next because it goes up to 5.5.
Our test will go 5.5.
Yes,
When is the test?
Monday after next.
What would Monday after next mean?
Not next Monday, but the one after that.
Monday coming, I'm going to do 5.5. A week after that, the test.
Okay, that makes more sense. I was like, the Monday next, I was like, well, what language are we talking in? Come on, let's start.
Okay, how do you figure out what the singular points are? You put it in standard form, right? This means that y double prime minus divide through by x squared. I get 4 over x. 4 over x squared equals 0. And so now I have to set the denominators equal to 0. This means x equals 0 is the only singular point. Right? Because 0 is the only thing that makes either of these denominators 0. And so what you do is you do this test, right? You plug in x naught for 0. So then we find the limit as x approaches 0 of x minus 0 times this function, minus 4 over x. Right? And that limit, of course the x's cancel. This gives you minus 4, which is finite. If we test the limit as x approaches 0 of x minus 0 squared, maybe I should be writing it out. Limit x minus 0 times this x minus 0 squared times this. Here the x squares would cancel again, and we get 4. So both these limits exist, and they're finite. This means x equals 0 is a regular singular point. So it says, determine and classify the singular points. We found the singular point, which is x equals 0, and we classified it as regular because these limits give us finite answer. Okay, so this one we are going to do a similar thing. write it in standard form. That's the standard form. Look at the denominators. What will make them 0? Well, x equals 0 again. X equals 0 is the only singular point. But what kind of singular point is it? We do the test. Take the limit as x approaches 0, x minus 0 times minus 4 over x. The result is minus 4. Take the limit as x approaches 0 of x minus 0 squared times 4 over x. The result is 0. These are both finite and they exist. Therefore, x equals 0 is still a regular singular point. It's a regular singular. A lot of times there's a question that just asks you to do this. Find the singular points, classify them. Right? This is how you do it. Just test these limits. Write it in standard form is the first step. See where the denominators are 0 is the second step. Any point where it's 0, that's the singular point. To figure out what kind of singular point, you do these limits.
Should that be 4 over x squared? Denominator of the second?
No, because this is x. There's an x here.
Okay.
There wasn't just a constant last time. Right? It's a very subtle difference, but okay, this one. First put it in standard form. Here we have 2x over x squared times 1 minus x squared. 4 over x squared times 1 minus x squared. Good? What were you saying? What's the question?
Why is it 0?
Oh, because
Equal to 4 more.
this is just x squared. The x cancels only one of them, so you have 4x here.
And then you get 0.
Okay, so now look where the denominators are 0. It happens at 0 and 1. So there are two singular points of this guy. Right? We have x equals 0 and x equals 1 are singular points. Let's classify them. You do it one at a time. So let's classify x equals 0. So what we're going to do is we're going to take the limit as x approaches 0 of x minus 0 squared, x minus 0 times this guy. So we're going to have 2x over x squared times 1 minus x squared. And what is that going to be equal to? Don't know how to write 0. So this x would cancel this x will cancel that x. Plug in 0, you get 2. So that's finite. Limit as x approaches 0 of x minus 0 squared times, now if I look at this guy, 4 over x squared times 1 minus x squared. This x squared would cancel that x squared. Plug in 0 now, I get 4, both finite. So this means x equals 0 is regular.
You will not have to go further than that.
No, just check these two limits and just whatever they give you, right? As long as it's finite, limit exists, it's finite, it's regular. So that's the case for x equals 0. Let's look at what happens for x equals 1.
Irregular. That's my guess. Irregular. That's my guess.
Why would you guess that? You don't guess here. You work things out.
We'll see.
Classify x equals 1. Which means we're going to do the limit now as x approaches 1, because 1 is the singular point.
Mm-hmm.
X minus 1 times this first function, 2x x over x squared times 1 minus x. And so this x will cancel that x. This would go into that minus 1 times. So this is just the limit as x approaches 1 of minus 2 over x times 1 minus x. And what happens as x approaches 1 there? Does not exist, right? It goes positive infinity from one side, negative infinity from the other side. Let x approach 1 of x minus 1. Well,
You don't even need to do that.
we don't even need to do that, right? Because they both have to exist to be regular. So we can just stop now. So as long as one messes up,
All
we're
of it
good.
messes up.
It's all or nothing. So x equal 1 is an irregular symbol.
Kind of like,
I should put money on it. I do.
You see, well, Jhevon wouldn't give us all regular single points. That's a very
I didn't say that.
I'm going to give you all single points. Just mess you up. Okay, we'll stop there.